doing where he said like, oh, the speed detective kind of like chooses who goes first. Yeah. Like, what if you accidentally make two characters like the same speed, then the first? You know what I mean? So, but it's okay. Um, so like, calculus is okay. Physics is pretty good. I think, you know, it's okay. Nothing crazy. Nothing crazy about it.
Okay, so I got the first one that worked.
Oh, great.
I put let's see in class, right, I put in the chat for the course that, if this doesn't, and I have to explain, oh my God, I was close and then expecting everything to work, and
Yeah.
then I realized I missed like a couple, like I had like a minus and a plus, so I saw it as soon as I was like, what?
Oh.
So it was very shocking to actually read, but, so that one's good. I'm now trying out, quasi-Newton graphs.
Oh, cool, great.
So it's, you have to get a lot of inputs though, right,
Yeah, yeah.
for that, if we were to, because you
Yeah,
have to
yeah.
bring it in 3 times each time.
Right.
Okay,
So actually, I'm changing course state a little bit just because, I want to make sure we do an example with another term. So I'm going to show you how to do it for actually this one too.
okay,
So I think that'll help with your quasi.
okay, awesome. And even for this one, because like, if we just didn't restrict the regional, so like I put the minimum here, that's gonna matter though, because we have that it must be 400. So with, at least to the dichotomous search, you could set that as your min and you don't need any like penalty terms.
Mhm.
For this one, it's a little trickier to do that. No, I do have some attempts, but I think this will help more because I just have the same sort of like scream at you and then you sold the value.
Yeah, I think they will help. Mhm. Yep. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. All right. So today I think this will probably be the last day that I'm going to be talking. So, I think all of next week we're just going to spend just doing a final project workshop. So that means that you guys can bring your codes. I can take a look and just kind of help you debug any questions that you may have. So I was telling this to my finite element people just on Tuesday too, that think of the two lectures next week as kind of like just office hours for you guys, right? So the final project, it involves a lot of coding, right? And so we've been practicing writing these algorithms for a while, but it's one thing to do it for an example for homework, but it's another thing entirely to do it for the project. And so I wanted to give you guys enough time next week to meet with me, work together with your peers too, and get your questions answered. So I'm still going to be available during finals week. I'm going to have my regular office hours. I'll be available over by appointment too. But I'm trying to take advantage of next week just because that's usually the best time to reach me. So I know quite a few people have started already, and so I've already been answering some questions. A lot of them over email, but some in class, some in office hours too. So definitely make sure you get started. At the very least this weekend, so you can come next week with some questions. Okay. All right, so the plan for today is I have just a little bit more of the lecture regarding penalty terms. Just kind of finishing up what we talked about on Tuesday. And then the other thing I wanted to do today was I wanted to work through an example with you guys on how to actually implement the penalty terms specifically for the final project, just because I know everyone's working on it. And so I thought it would be really useful to kind of see it kind of worked out in real time, how to incorporate this into the objective function for the final project, and then write kind of an example code for you as well. Because there's a lot of nuance in terms of how to use the simple trust function and the big trust function. That's where most of the questions I've been getting recently. So I wanted to show you kind of how I recommend how to use those functions. And whatever code I write today will be posted online for you to see as well. Okay. All right, any questions I can answer before we get started? Okay, all right, so let's pick up where we left off. And so last time we were here, we were talking about penalty methods. And penalty methods, their main purpose was to enforce constraints in nonlinear programming algorithms. Okay. So just to kind of refresh your memory, the whole reason we're kind of going down this path is that all of the nonlinear programming algorithms, or all the NLP algorithms that we've learned so far, things like Monte Carlo, random walk, coordinate search, dichotomous search, we've gone through, maybe about a dozen of them. None of those have any capability for incorporating constraints into the algorithm. Okay. So, for almost the entire second half of the class, we've kind of ignored the fact that constraints exist and constraints are a thing. So we need to bring that back because constraints are actually a really important part of our algorithms. Okay. And so, the strategy that we're using with the penalty terms is to say that, let's take all of our constraints. All of our constraints have a mathematical form already, and let's incorporate them directly into our objective function. So for example, or not for example, here's the general form, okay? So the idea with penalty methods is to form basically a new objective function, which we'll call the augmented objective function. Okay. Our augmented objective function contains our original objective function. Right, so that's what we were originally trying to optimize, plus some penalty terms. Okay. So if you remember from last time, we had separate penalty terms for our inequality constraints and separate penalty terms for our equality constraints. I'm just going to consider the inequality constraints now, just because there's usually an easier way to deal with the equality constraints. Okay? And so, what is that? A multiplied by summation j is equal to 1 to m of gj x hat squared. Okay, where this capital G here, this is our function of our inequality constraints. And so last lecture, we spent most of the time talking about what this looks like. So if you recall from last time, this gj here, that's where we use our max function. Okay. So I won't go through that again, although we'll see examples of that being used later today. Okay. But the one mysterious parameter that we haven't really talked about all too much is this guy right here. Okay. So this A is not it's not just a mystery number here. We call this our penalty parameter. And right at the end of class last time, we basically said that the value of the penalty parameter determines how strictly we're going to enforce the constraints. Okay. Basically, the higher the value for our penalty parameter, the more strictly the constraints are going to be enforced. Okay. Because we kind of left Tuesday with kind of a somewhat alarming fact too, which is the fact that with this penalty method, we're actually not guaranteed to satisfy all of our constraints. Okay. It is very possible to use penalty methods and to get an optimal solution and to look and say, wait a minute, one or more of my constraints are actually violated. Okay. So if you use a low value of the penalty parameter, so let's say you use A is equal to 0.1, something like that, then it is actually very possible that your objective function is not going to follow these constraints. Okay. All right. So of course, that begs the question of, then why don't we just jack up A as high as we can? Why don't we just make A 1 million, right? So I guess first let me say, so the higher the value of the penalty parameter, the higher that number is, the stricter the penalty is going to be for violating the constraints. Okay. And what is a penalty for an optimization algorithm? Well, remember, an optimization algorithm always aims to minimize the objective function. So if you increase the value of the penalty parameter, it's going to make your objective function much, much higher, which is a big penalty for the objective function. Okay. So of course, why don't we just maximize A as much as possible? Why don't we just make it, 1 billion? Well, there's some limitations in terms of that. If it were that easy, then this would kind of be trivial. Okay. Okay. So I've kind of scrolled back up here to kind of show you our augmented objective function, because I want you to kind of think of this as a comparison between the two terms here, right? So we have our original objective function and we have our term with the inequality constraints. Okay. So actually, let me put a box around both of those just to kind of highlight the fact that we're kind of comparing these two things. So these two terms here are kind of competing. You can think of them as kind of competing for attention in the original objective function. Okay. Now, the thing ultimately that we want to optimize is this one, right? So the original objective function is that's what we actually want to find an optimal solution for, right? The constraints are only merely there just to make sure that we have a valid solution. Okay. So what happens when you pump up A really, really large? And so if you pump up the value of A really, really high, okay, what's going to happen then is that your penalty terms will start to dominate the entire objective function. Okay. And so, yes, if you pump up the value of A really, really large, you're going to get a solution that satisfies all your constraints. Granted, your algorithm is working properly, right? And that's fine. But a lot of times you want something more than just a solution that complies with the constraints. You want something that's actually going to be truly optimal within those constraints, right? And so if you pump up the value of A too much, you start to kind of dwarf out the original objective function, and then it starts to really not become a factor in your algorithm. Okay. And so if you make it too high, the original objective function kind of gets dwarfed out. Okay. And then so the consequence of this is that you'll end up with a compliant solution, a viable solution, but it just may not be optimal just because your original objective function just did not really play a role in the algorithm. which, of course, isn't the worst thing, right? And so, just getting a viable solution oftentimes is halfway there. That's half the battle. But, the whole point of running an optimization algorithm is to find one that's actually truly optimal. Okay. There's other mathematical reasons why you can't just pump up the value of penalty parameter. Ideally, your objective function should be a fairly smooth function. And so if you pump up that penalty parameter really large, you end up with a very, I guess, discontinuous function, which is not good. So most algorithms kind of assume that you have a smooth function. So, there's a lot of mathematical reasons why you can't do this too, but I think this is kind of the easiest to kind of interpret reason where, you don't want to phase out your original objective function. You want the penalty parameters to be there just enough so that you ensure compliance, but not so much that it dominates your entire objective function. Okay? So there's kind of a delicate balance. Okay. All right, any questions on that? Okay, good. All right, so then that kind of asks another question of, what is a good value of the penalty parameter? We know it can't be too low. If it's too low, then we're not going to get compliance with our constraints. It can't be too high, otherwise it's going to phase out our objective function. So there should be some Goldilocks region or some region that's just right for that penalty parameter. Okay. Well, the unfortunate answer that I have for you is that it really depends on the problem, which is the catch-all political answer for every problem in society. Okay. It's really hard to tell, when you're coming up to a fresh optimization problem, one that you've never done before, what's an appropriate amount for the penalty parameter, because it just depends on so many other factors. So, the way to kind of approach this is to use kind of an iterative approach or kind of a guess and check approach. And there's a very specific strategy for that, which we're going to go over right now. Okay. Okay, so let me rewrite our formula for the augmented objective function just so we can see it again. Okay, so that's our augmented objective function, and what we want to find out here is how do we determine the value of A? Okay. Okay. So if A is too low, okay, if A is too low, then we're going to get a solution that does not comply with our constraints. Okay. But if we choose a value that's too high, okay, if we choose a value that's too high, our original objective function gets phased out, and we end up with a compliant but not necessarily optimal solution. Okay. And in some of the worst cases, you might just end up breaking your algorithm. It just may not work. Okay. Okay, so what's the solution here? So the solution is actually to sequentially vary the penalty parameter over and over and over again until you get a compliant solution. Okay, so there's actually a lot of really interesting strategies with this. Some people, they may start with the penalty parameter that's too high and then bring it down. Or you can go the other direction. You can start with the penalty parameter that's too low and then bring it up. Okay. Question.
Would there ever be multiple values for A, like in our case where you have like displacement as well as like cost?
Oh, yeah, yeah. Yeah, and actually there are some constraints which, may be more difficult to comply than other ones. So you may put different penalty parameters for different constraints as well. And so I'm just doing kind of a general one here for the overall question.
So the different is sort of like A, B, C, or the
Yep.
A1?
Well, I mean, they're all just gonna be numbers in the end, so you can call them what you want. Okay, so like I mentioned, there's two strategies to this, and so you can go low to high. Okay, and so the low to high strategy is that you start with a small value of the penalty parameter, run your optimization. Okay. Okay. So starting with the low value of the penalty parameter and running your optimization, odds are you're likely going to get a result that's non-compliant or non-viable. Okay. So what is a low value? A low value might be something like 0.1, right? And so 0.1 is kind of a decent starting point. Again, it's going to depend on your problem, but that's not a bad place to start. Okay. Okay. So then what you're going to do from this point is that you're going to take the result of this optimization, which we know is non-viable. Okay. And by result of that optimization, I mean the values of the design variables that you ended up with. Okay. You're going to take that result and use that as the starting point for a new optimization, except you're going to crank up the value of the penalty parameter, a little bit. Okay. So, let's say that you start with a penalty parameter of 0.1, you run your optimization, you get a result that's fairly, that's optimal, but may not be viable. So you take that as a starting point and then you rerun it, but you increase the value of the penalty parameter just a little bit. So maybe you go from 0.1 to 0.5, and then you do that again. And so you increase, you're basically slowly increasing the penalty parameter until you have a result that's compliant. Okay. Okay. So the nice thing about this approach, the low to high approach, is that you're much more likely to land on an optimal solution just because every single part along the way, the original objective function is kind of dominating your entire algorithm. Okay. And then you basically sequentially vary this penalty parameter going up until you reach one that's compliant, and that compliant solution is also going to be optimal. Okay. So that's the low to high approach. The low to high approach, you start low and then you increase it until you reach a compliant one. Okay. All right. The other way to do this is, of course, to go the other direction, to go from high to low. Okay. So the high to low approach is basically the exact same thing, except instead of starting with a low value of the penalty parameter, you're going to start with a very large value. Okay. So you start with a high value and then you bring it down over successive optimizations. Okay. The stopping point for this one is actually the opposite. So with the high to low approach, you keep reducing the penalty parameter until you find a result that's not compliant. Okay. So you stop when you get a result that's not compliant, but you don't take that one as your optimal solution. You take the previous one, the one that was still compliant, um, and somewhat optimal. Okay. 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 So two approaches here. We have the low to high approach and then the high to low approach. Which one is better? Well, so depending on the form of your penalty terms, different strategies are going to be more effective. So the penalty term that we are using in this class is using that max function. So it turns out when you're using that max function, the low to high approach is actually going to give you better performance, or it's going to be a little bit easier to implement. Okay. There are other forms of the penalty parameter. Some of them use a logarithm function, and the high to low approach may work well for that one. But for our purposes, I only kind of taught you one form of the penalty parameter. The low to high approach is going to work a bit better. Okay. So next thing I'm going to do after this is I'm going to shift over to the final project. And so I will show you actually how to implement a low to high approach within the final project. And in fact, I'm actually going to write an algorithm from scratch so that you can see kind of every aspect of the final project, which is using all the functions, formulating your objective function, making the penalty terms, and eventually, we'll implement this low to high approach. Okay. Any questions before we kind of shift gears a little bit? Okay. All right. So let's go to the final project. So hopefully this will be helpful. Of course, hopefully it'll be helpful for the simple trust, but a lot of how we do things today can be applied for the big trust as well. Okay. Okay. All right, so for your final project, I've given you two optimization problems to do. So one is a simple truss, which is a two-dimensional truss with only two design variables, and a much bigger truss, which I believe it had six design variables. Okay, so the simple truss looks something like this. And so we have basically two fixed points here. We have kind of a square structure like, or rectangular structure like this. It's filled with all truss elements. You can see that there's no element here. Okay. So this is our truss structure for the simple truss. Okay. Let me go ahead and label all the nodes as they are in the final project. So this is node 1, node 2, node 3, node 4, node 5, and node 6. Okay. All right, so the way we parameterize this structure is we have two design variables, one of them being the height of this structure, so we call that parameter h. And then we have the lengths of each of these square sections. So we have this length here and this length here. Okay. All right, so we have our two design variables. Okay. We have one, which is the height of the structure, which has the symbol h, and two, the length, which has the symbol L. And then on this truss structure here, we are applying forces. And so we have a vertical force on node 4 and a vertical force on node 2. Okay. Where P has a magnitude of 10,000 pounds. Okay. So what's going to happen here? So just like any elastic structure, if you apply loads to it, you constrain it to a wall, it's going to deform, right? And so in this case, we have two forces here that are dragging the truss structure down, and so the entire structure is going to kind of bend down into the right. Okay. So what do we want to do? So the objective of this problem here is to optimize the values for H and L. Okay. Basically choose optimal values for our two design variables such that the overall deformation of the truss is minimized. Okay, so we have a very classical kind of minimization problem here. We have two design variables, and this is kind of our objective. Okay. We have constraints as well. So before we kind of move forward, let me go ahead and list out all of the constraints. Okay. So there are three constraints that are explicitly listed in the document itself, and each of our design variables here, H and L, have an upper bound and a lower bound. Okay. Okay, so let's start with the stated constraints. Okay. Okay, so if you go into the documents for our final project, you'll see that the first constraint is that the total horizontal length of the structure cannot be shorter than 400 inches. Okay. So this one's pretty straightforward, and so we can compute the total horizontal length of this structure here, right? And so we go back up to the figure. The total horizontal length is L plus L, or 2L. Okay. So the mathematical form of this is that 2 times L, which is the total horizontal length of the structure, has to be greater than or equal to 400. Okay. All right, so that's kind of step one, when you're doing your big truss problem, is to take each of the constraints and write out its mathematical form. And another thing that you can do is you can put it in standard form as well, just because it's going to help you when you're forming the penalty terms. Okay. So the standard form for this constraint. Notice this is an inequality constraint, and so standard form is we have g of x is less than or equal to 0. Okay, so we basically have to get 0 on one side of this expression, and it has to be on the on the right of the less than or equal to expression. Okay. Okay, so to get this in standard form, I'm going to divide this entire equation by 2. Okay, so we have L must be greater than or equal to 200. Okay. We want the 0 to be on the, in this case, we have a greater than or equal to sign. So one thing we can do just to make it easier for us, let's swap these. And so let's put the 200 on the left. All right. So let's say that 200 must be less than or equal to L. Okay, so that expression is exactly the same as the one above it. I just kind of mirror flip the entire thing. Okay. Okay. And the other thing I'm going to do here, just to get a 0 on that side, is I'm going to subtract L from both sides. Okay. And so if I subtract L, we get 200 minus L must be less than or equal to 0. Okay, so that's a standard form of that constraint. So that's going to be really helpful for us once we form our penalty terms. Okay. Okay, second constraint. Second constraint from the document says that the ratio of the height and total horizontal length must be 0.4. So, first question you should always ask yourself when you see a constraint, you should first classify it as an equality constraint or an inequality constraint. Okay. And so if you read this constraint here, we see that the ratio of the height and total horizontal length. So let's actually write that as an expression first. Okay. So the ratio of the height to the horizontal length, that's h over 2L. Okay. The other kind of operative word here that's kind of different from the first constraint is that this must be 0.4, right? So there's no leeway here. That must be true. Okay. And so for an expression that must be true, that means we are going to use an equality constraint. So h over 2L must be equal to 0.4. Right? So that's good. So actually equality constraints are great for it because what we can do from here is we can do direct substitution. And in fact, our expression for direct substitution is quite simple in this case. Okay. And so I'm going to multiply 2L by both sides. And so if we do that, we get h is equal to 0.8 times L. Okay. And then just after one algebraic step there, we have our direct substitution expression. Okay. And so no matter what we get from L, from this optimization, H is going to be 80% of that, okay? And so, when we do form our objective function, we're just going to simply plug in H is equal to 0.8 times L, okay? And that's really, really good for us because, if you look at our original optimization problem, we had two design variables. We know that when we use direct substitution, it reduces the number of variables by one. So now we have a one-dimensional optimization problem, which is fantastic. We have so many methods to use for that. Okay. Okay. Number 3. Number 3 is going to be a little bit interesting just because we don't have all the information to account for this just yet. But we are going to do that once we combine it with the code. Okay. The third constraint is that the maximum force of force experienced by any element cannot exceed 300,000 pounds. Okay. So that one seems a little bit interesting because force is not one of our design variables. Our design variables are just H and L. But we are going to be able to compute force by running our truss simulation. Okay. So the maximum force in this case is what we call a derived quantity. So that's not something that we have direct access to just based on the values of the design variables. Okay. We can still use it. It's just that, for any derived quantity, remember, we cannot take derivatives of it. Okay. So this derived quantity in this case is computed from the truss simulation. So we'll be able to use it, but only in kind of an evaluation kind of way. So, the fact that we have force here just kind of, it forces us, I didn't intend for that to be a pun, but it just ended up being, it forces us to use a nonlinear programming policy. Okay. What's going on outside? Okay. All right. But we can still write a mathematical form for this, right? And so the mathematical form for this is that the maximum force, which we're gonna compute that in some way later on, but we'll keep a variable for it, okay, must be less than or equal to 300,000. Okay. So same thing here. Before we move forward, let's put this in standard form. And so standard form is basically we're going to put a 0 on one side of the equal sign. So I'm going to take 300,000 and subtract it from both sides. Okay. We have F max minus 300,000 must be less than or equal to 0. And that's the standard form for that. Okay. So we have 3 constraints. 2 of them are inequality constraints, and so we put them in standard form. And then our third constraint, well, I guess our second one here is our equality constraint, which we're going to use for direct substitution. Okay. All right. Any questions on how we obtain these so far? Good. All right, but those aren't the only constraints that we have. And so we also have constraints on the upper and lower bounds of each of the design variables. Okay. So the project specifications also tell us that each of our design variables, H and L, have a lower bound, so the lowest admissible value, and an upper bound, which is its highest admissible value. Okay. So for H, okay, H has to be between 80 inches and 400 inches. Okay. And L has to be between 100 inches and 500 inches. So each of these, each lower bound and each upper bound is a separate constraint. So this actually adds 4 more constraints to our problem. They're all fairly simple. Okay. So let's write the standard form for all 4 of these constraints. Okay. Okay. So let's do the constraints for H first. And so first one we have is that 80 minus H has to be less than or equal to 0. Okay. The other one is H minus 400 has to be less than or equal to 0. Down here for L, we have 100 minus L has to be less than or equal to 0. Okay. And then also L minus 500 has to be less than or equal to 0. Okay. Okay. Good. So these are all the constraints for the problem. I'm going to give you a little bit of a pro tip here, just to help save you some typing. Okay. So we know already from our previous constraints that the value of H is basically tied together with the value of F, right? So H and L are connected by an equality constraint. So that means that, whatever you determine for one of them is going to set the other one. So, it's kind of not really necessary to have all of these constraints here if one of these variables are going to be dependent on the other. Okay. So you can solve this either way. So you can make H your primary variable and solve for L, or you can make L your primary variable and solve for H. Okay. So the way I've kind of formulated this problem is I made L my primary variable. Okay. So since H and L okay, H and L are connected by an equality constraint. We don't need an upper and lower bound for both of them. Okay. So what I'm going to do is I'm going to make L my primary variable just because I know something else about the problem too. So I'm going to go ahead and cross out these 2 constraints on H. Okay. Just because once we have the value of L, then our value of H is already determined. So we can save ourselves a little bit of writing and not worry about those constraints on H. Okay. Okay. One other thing that I'm going to do here is that I noticed that our constraints here are a little bit redundant. Okay. And so if I scroll back up here and we look at the very first constraint that we have here, right? We have this constraint that 200 minus L has to be less than or equal to 0. Okay. Or in other words, L has to be greater than or equal to 200, okay? This looks a lot like a lower bound constraint. Right? So because we're constrained by the fact that the total horizontal length has to be greater than or equal to 400, that means the lowest value that L can be is 200, okay? That's actually redundant with our other lower bound constraint down here, right? So our other lower bound constraint says that L has to be greater than or equal to 100. But if L already has to be greater than or equal to 200, then that makes this constraint basically redundant and kind of obsolete, okay? I'm going to go ahead and cross out this one right here, just because this one is redundant. Okay. So that means the only bound constraint that we have to worry about from, at least from this part, is just making sure that L is less than 500. Okay. All right. Any questions on that? Good. All right. So for the objective function itself, right? We only have one objective in this problem. And so our objective is to minimize the total deformation of the structure, okay? So just like the force, deformation is not something that we can compute directly from the design variables. So that's something we have to run our code, okay? So total deformation, just like the force, this is a derived quantity. So it's something that we're going to have to run the code for to do. But we'll take note of it for now, and then incorporate that into our code. Okay. Okay. So with that, we have about 23 minutes left remaining. So I'm gonna go ahead and jump into MATLAB and show you basically how to incorporate all of this information. Okay. Okay. So let me go ahead and share screen here. Okay. So if you go to Canvas, you'll see that I posted one example for you to look at, which is a Monte Carlo implementation of this algorithm. Okay, so there's some useful things here, and so on the one hand, it shows you how to do the direct sub, but one thing that you'll notice is missing is that this implementation does not take the penalty terms into account. And so I wanted to make sure I do an example for you, which I show you how to actually incorporate those penalty terms. Okay. And so to help kind of illustrate this and to kind of show you kind of a good strategy that you can use for the project itself, I'm going to show you how to basically take one of our other example codes and then basically, fix it around or basically modify it to help with this, with this final project. Okay. So I'm gonna take basically the simplest example code that we have, which was unrestricted search, and I'm going to show you how to modify this to work with the final project. Okay. Okay. So I'm gonna go ahead and make a new script. Let me go ahead and save this, and we'll call this simple. Let me call it EGME 434 final project simple example. And I'll post this code online just for you to see too. Okay, so first I'm going to add these lines up here, clear all, close all CLC, just because that's how I learned MATLAB 15 years ago, and it's kind of ingrained into my brain to start every script with that. I know it's not necessary, but the script doesn't look right unless I have that. Okay. And what I'm going to do is I'm going to first copy and paste all of the code that was from this unrestricted search. And we're going to modify this to, to work with our final project code itself. Okay. Okay. So I've copied and pasted the code for unrestricted search here. Okay. So first thing we're going to do here is we're going to kind of take stock in terms of how this code works. Okay. And so if you recall, unrestricted search was the first nonlinear programming algorithm that we went over. And basically the idea with unrestricted search is to check every single value of the objective function, and then over a certain range, and then just give you the maximum from, or give you the most optimal from. Okay. Okay, and so just because it's not written here, let me go ahead and list out what the objective function for this script was. Okay. Remember, this script was just copy and pasted from before, so we're working with a different objective function. Okay. And so the objective function for this problem was x times 1.5. Okay. Okay, so the first thing I'm going to do is I'm going to identify every single location in the script where we basically compute the objective function. So let's first identify every location. Okay. So basically everywhere that you see the function x times x minus 1.5, let's go ahead and mark it. And just to make things a bit easier for us, let's mark it with a particular marker. Because we're not going to be computing this objective function anyway. So let's just replace it with an instance. So we'll replace each instance with. So I'll just call it the objf. Okay. Okay. First thing we have here is we have this one right here. So this obviously is a computation of the objective function. So I'm going to replace this with objf. Okay. Right, and I use all caps just to make it easier for us to see. Okay. Here we have two more computations of the objective function. So one is in the plus direction, one is in the minus direction. We'll deal with that in a second, but we're going to go ahead and replace this with objf. Okay. And this one we're going to replace with objf. Okay. We don't have any objective function here. And then finally, we have another objective function here. Okay. I'm going to replace this with obj. Okay, so we have 4 locations in the code where we're calling the objective function. Okay. All right, so first thing I'm going to do here, the first code that I'm going to write is I'm going to write a wrapper function or a helper function that's going to compute our objective function. So let's, let me take off caps lock. Okay. Because our objective, we know that our objective function is going to be quite complex in this case. But not only do we have to run the trust code itself, not only do we have to run the trust simulation, we also have to incorporate all of our penalty terms as well. Okay. So just to make things convenient for us, and so I've seen people kind of compute the objective function within the code itself, and I don't blame you for that because that's how I've implemented this Monte Carlo example. But for your project, especially for the big trust, I highly recommend that you write a wrapper function just to make things kind of simple for you. Okay, because you're going to be calling this objective function many, many times in the code, so it really kind of helps to write this wrapper function. Okay. And so to write a wrapper function, actually, let me go ahead and give myself a bit more space here. Okay. And so we've done this for a few examples. So basically, we're writing a special function within MATLAB itself. Okay. Okay. So the way it works is we're going to do func is equal to, or I'll call this obj is equal to function. Okay. We have to give it a name. So I'll call it obj func. Okay. So our objective function for the simple trust has 2 design variables, L and H. And so I'm going to make those 2 arguments, L and H, not hold, H. Okay. Okay. So there is our objective function. Okay. Okay. So remember, the purpose of this wrapper function is to take all of the design variables and compute the value of our objective function. Okay. All right, so first thing I'm going to do, just because we're going to need that information to compute all our constraints in our objective function, first thing I'm going to do is I'm going to run the trust simulation based on these values for L and H. Okay, so to do that, I'm gonna come back to this simple Monte Carlo example here. And I'm just gonna copy this function right here. Okay. So you can see here that this one line right here is gonna run our trust simulation. And so it takes in our two design variables L and H, and it returns two variables. So it returns one vector called E forces. Remember, E forces is a vector that that contains the forces of all the elements in the truss, and it also returns this vector here called displacements, which contain all the displacements of each node in our truss as well. Okay, so we're going to use both of those, both of that information. Okay. All right. Next, because we're going to use them in our objective function, let's compute all of our penalty terms that we just finished computing. Okay. So we have basically one penalty term that's associated with each inequality constraint in our problem. Okay. Okay. So first one that we have is the constraint on the horizontal length. Okay. So this is going to be constraint 1, which states that 200 minus L has to be greater than or equal to 0. Okay. Okay. We'll call this penalty 1 is equal to 200 minus L. Okay. Right. But remember, the way that we do this is we use the max function. Okay. So since this is an inequality constraint, we're going to go max between 0 and this. Question? Yes.
L version the other way.
Oh yes, yeah. Thank you. Yeah, 200 minus L has to be less than or equal to 0. Okay. So remember, we use the max function here because if our value here is satisfying the constraint, then we don't want to penalize our objective function here. Okay. So this is kind of what we talked about on Tuesday. And so in this case, this constraint sets a lower bound for the value of L. And so if our L is greater than 200, so let's say that we have an L value of 300, that's a perfectly valid value for us. We don't want to penalize our objective. Okay. Okay, so that's our first constraint, and that's our first penalty term. Okay. Remember, we're going to use direct substitution for our equality constraint. So I'm going to ignore that one. Okay. So our second constraint here is a constraint on the maximum force. Uh-oh. Okay, so our second constraint here says that the maximum force must be less than or equal to 300. So we have F max minus 300,000 must be less than or equal to 0. Okay. Okay, so for this constraint, we need to use our E forces vector here. Okay, and we basically need to compute the maximum of that force. Okay. So I'm going to use this this code here from this Monte Carlo. Okay, so this line of code here basically takes our E forces vector and computes the maximum. Okay, I'm going to copy this code here. It goes right here. Okay, so now max E force is a variable that contains the maximum force within our truss. Okay, so now we can form our second penalty term. We have penalty 2 is equal to max 0, comma, max E force minus 300,000. Just make sure I have enough zeros there. Yeah. Okay. So you can see, putting your constraints in standard form is really helpful because then you can just plug it right into these constraints. Okay. Next we have constraint 3. Okay. So the only other constraint that we have is the upper bound constraint on L. So basically it's L minus 500 has to be less than or equal to 0. Okay. So we have penalty 3 is equal to max 0, comma, L minus 500. Okay, so that's it. So that's how you incorporate the penalty terms, or that's how you compute the penalty terms in MATLAB. So make sure you kind of use this. Well, you can literally use this for the simple choice. Okay. Okay. Now that we have all of our penalty terms computed, we can compute our objective function. Okay. So our objective function in this case has two parts, remember? And so we have our original objective function. So our original objective for this truss problem was to minimize the total deformation of the truss, okay? And so to compute the total deformation, I'm going to come back to the Monte Carlo code. And you can see here in the Monte Carlo code that there is a line here to compute the total deformation of the truss, okay? So I'm just going to copy this over here. Just like that, okay? So this line of code, d total is equal to sum vec norm of displacement. This computes the total deformation of every node in the truss itself, okay? And so if you notice in the Monte Carlo code, this one expression here, this one expression formed the entire objective function because we were using a different way to check the constraints, okay? But because we're switching to the penalty method, our objective function is going to be not only this, but it's also going to contain all of our penalty parameters as well. Okay, so our objective function in this case is obj. Okay, it's going to be equal to. Okay, we have d total. So d total here, this is our original objective function plus a multiplied by all of our penalty terms. Okay, so penalty 1. Remember, each of our penalty terms we have to square them. So we have penalty 1 squared plus penalty 2 squared plus penalty 3 squared. Okay. Or oh, thank you. Squared. It's hard to talk and type and look and see what you're typing at the same time. Okay. All right. So that's our objective function. Okay. And actually, let me just make sure that I have the right form for this. Forgot the syntax for an inline function. I know I used it in code somewhere. So I think I use it for the 1D cases. Nope. Quasi. Oh, okay. Oops. I was wondering why it was giving me a red underline here. There we go. Okay. All right. So that's our objective function. So basically everywhere that we see, everywhere that we marked in the code above where we're computing our objective function, let's go ahead and replace it with this. Okay. Okay. So first thing we have here is we have objf. So let's replace this with obj func. Okay. And let's feed in our two design variables here, L and H. Okay. Of course, you know, we don't have values for these just yet. So let's go ahead and define these. Because instead of X being our design variable, L and H are our design variables now. Okay. So I'm going to say set L naught. Let's set L naught equal to 200. So let's set L naught 300. Okay. H naught we know is directly related to the value of L. So I'm just going to say H naught is equal to 0.8 times L naught. Okay. And then let's plug that in here. Okay. Good. Okay. Next, we need to plug those in here as well. Okay. So once again, I'm going to replace these objf with this. Okay. But remember, this is checking whether we should go up or down. Okay. And so for this, we're going to add L naught plus step. This one, we're going to do L naught minus step. Okay. And we actually have to update the value for H as well. Okay. So instead, let me do this. Remember, the value of H, even though we have two inputs for our objective function here, the values for H and L are linked together. Okay, so I basically replaced H here. So, for up here, we computed H separately, but since we're kind of, saving a little bit of space here, I've included that directly into the objective function. Okay. Okay. And I think all of these can be left alone. Actually, this one here, we need to replace this. So instead of our design variable being X, our design variable in this case is H, okay? Or excuse me, it's L. We have L test is equal to L naught, okay? All right. And so while F test is less than F best, okay? We can basically say that this, so we're going to replace this by this. So L test, X test is going to become L test plus step. And then when we compute our objective function, we're going to use this one. Okay. Okay. Found at L is equal to. Okay. Sorry, I know I kind of changed a lot there without really narrating it, but all of this was just kind of cleanup stuff just to make sure that, because our objective function here is different, because our design variable is different, I just had to change the variable just to make sure it all kind of fits together. Okay. Okay. All right, so we should be good to run the code. The only thing that we're missing here is our penalty parameter A. So let's go ahead and specify that up here. Specify the value of the penalty parameter. Okay. So let's set A is equal to, let's start with 1. Okay. Okay. All right, so let's go ahead and run this code. Hopefully we don't get any errors. We got one error here. Let's see, undefined value A. Oh, we need to define within the function itself. So all this is off the cuff, by the way. I only really decided to do this kind of 5 minutes before the lecture, so that's why it's a little bit disorganized. But we'll go through this again on Tuesday. Okay. All right, so we ran the optimization and we ended up with an optimal value of L of 299.9. Okay. Okay, I don't know if that's the actual optimal value. I think it's actually not. We'll debug this code on Tuesday. Okay. All right. Any questions on this? Okay. All right. So we'll pick this up again Tuesday. And so I know that was a little bit disorganized. So I'm going to upload this to Canvas. We'll talk about it again on Tuesday, but hopefully, that whole all that tutorial on how to form the penalty terms and incorporate that into your objective function, at least how to form your wrapper function here. Hopefully that's useful to you guys for the final project. So I would definitely recommend this approach. And then, incorporating that into the algorithm, we'll clean this up on Tuesday. Okay. All right. So thank you guys for coming today. I hope you guys have a good weekend and I will see you guys next week. Yeah.
Like the lower space of the.
Oh, yes.
The.
Yes. Mhm. Do you have to use the penalty function for the simple truss? Well, if you're gonna use one of the 1D optimization, algorithms, then, you probably have to use it, just because all of those are unconstrained methods, so. Yeah, unless you're using kind of a derivative of Monte Carlo. Monte Carlo is really the only method that you can use that where you don't have to use the penalty.
This one, like.
Oh, yeah, yeah. Yeah, that's right. Mhm. You're looking for FEA?
Yeah.
Sorry, get them over there.
Find it for that. So like you can go the plugin to provide to open this. Okay, the first one, that is the big one. So that's only the person rate and the equipment.
Okay.
And the second one is that you have a dynamic process, acceleration force, and the impact force at the end of the line.
Yeah.
Is that okay? So
Yeah. Yeah.
no, yeah.
Sounds great. Do you have a slide for the therapy?
Yeah, I found it from Google.
Oh, perfect. Yeah, yeah, perfect.
Okay. The one.
Oh, good. Yeah, that looks good.
Yeah. Okay. Thank you.
Yep.